here's a linear equation. If we want to graph this linear equation in 2 dimensions, it's not a big challenge. The x-intercept is 3, the y-intercept is 2, and we know it's a line in 2 dimensions. That should be a straight line. That's the best I can do. So here's this line, a graph of this line, assuming we're graphing in 2 dimensions, pardon me. And we can find some points on the line. So we already found 0, 2, and 3, 0, and we could also find, say, 1. If you plug in 1, you're going to get 4/3 there. Or we can go in the other direction. Let me put it over here. If you plug in -1, you're going to get 8/3, and maybe another one this direction. If you plug in x equals 2, you're going to get 4/2. And so we could come up with lots and lots of points on this line, and we can find the slope of the line. And the slope, the easiest 2 points to find the slope with would be this point, the intercept. So the slope would be, if you go from this point to this point, from 0, 2 to 3, 0, the rise would be -2. The run would be +3, and there's your slope. And that's going to be the slope no matter which 2 points you pick to compute the slope and which direction you go. So if you went from this point to this point instead of this point to that point, the rise would then be +2, the run would be -3, so you'd still get that -2/3. Or if you went from this point to this point, the rise is going to be -2/3, the run is going to be +1, and so you're still going to get that -2/3, or from here to here, or whatever 2 points you pick to compute that slope. Doesn't matter, because the slope is what it is. It's built into that line, and it describes that line. So if you have 1 point on the line, if you know this point is on the line and you know this is the slope, you have all of the information that you need to find that entire infinite set of points. So you just need the 2 bits of information there. So in 2D, the graph is a line. What about in 3 dimensions? The graph is what? So if you're in 3 dimensions and you want to find some points, so your points are now going to be x, y, z, ordered triples instead of ordered pairs. And for every point you have on this 2-dimensional line, say you take the point 0, 2, 0, 2, x equals 0, y equals 2, z could be anything. So you could take z equals 0, or z equals 1, or z equals -1, or z equals anything. So if we leave this as your x-axis, and this as your y-axis, and your z-axis is coming out up positive and down into the table negative, then this point would be right here, because it'd be x equals 0, y equals 2, z equals 0. This point would be sort of floating above that point. 1 unit up would be up here. This point would be down inside the table, 1 unit below. And every point on this line would have infinitely many points above and below it in the x direction. So this graph in 3 dimensions is going to be like if you take that line and you bring it infinitely up and infinitely down, you're going to get a plane that looks like this. So a linear equation in 3 dimensions is a plane. And that's kind of interesting. So let's look at another equation, a linear equation, this time with all 3 variables showing. So let me do plus 3y minus 2z is equal to 5. Okay, so this is a linear equation. It's got all 3 variables showing, so it has to be a 3-dimensional graph, and it would be a plane in 3 dimensions. And so we can find some points on the plane. Like an easy one to see is 1, 0, 0, because you plug in x equals 1, 0, 0, you get 5 times 1 is 5, plus 0 minus 0 is just still the 5. And then we have 1, -2, -3, right? So that would be 5 minus 6 plus 6 is still 5, yes. And then if we did 0 and 1 and -1 here, we'd get 0 plus 3 plus 2 is 5. So there are 3 points on the plane. And you could come up with a bunch more just by, guessing and checking or plugging things in and solving. You could come up with lots of points. So now we have these 3 points on this plane. I'm just going to use this set of coordinate axes since I already have it drawn. So this point, if you had the z-axis coming out, this point would be 1, y is 0, so you're not moving anywhere this direction, and z is 0, so you're not moving anywhere this direction. So it would be this point right here, which would be easy enough to draw in your x and y plane. This one you're not going to be able to draw in your xy plane because you're going to go 1, -2, and then you're going to have to go down into the table 3 units. And similarly here, you're going to have 0, 1, and then you're going to have to go down -1 into the table. So these are going to be hard to plot on a 2-dimensional surface because they live in the 3-dimensional space. But let's say I have that plane that contains these 3 points, and I twist my coordinate axes so that these points are right in the plane I'm looking at. I'm going to call this 1, 0, 0. I'm going to call this one 1, -2, -3, and then 0, 1, -1 I'm going to put right here. So we can't really talk about a slope when we're talking about a plane because, when you're moving, if you're a little person on this line, and you only have 2 directions you can go. You can either go this way or this way, and you're always moving on that line, and so you're always moving sort of according to that slope. But if you're on a plane, let me pick up and use this plane. If you're on this plane, if you're moving this way, you're moving up and down at a certain rate. If you're moving that way, it's a different rate. If you're moving this way, it's a different rate. And so there's no real way to talk about the slope of a plane. You'd have to be on a particular line on that plane in order to be able to talk about just a slope. But what we can do is we can come up with 2 vectors that live in that plane, and then if you have a point in that plane, say it's right here, we attach the vector's toes to that point. This point and these 2 vectors, which are called direction vectors, will get you the whole plane, because if you're sitting on that point and you want to get somewhere else on the plane, you go a constant multiple of this vector and a constant multiple of this vector, then you can get everywhere you want to on that infinite plane. So I'm going to come up with 2 direction vectors here. Let me do, say, this direction vector and this direction vector. So I'm going to call this one D1 and call this one D2. So the direction vectors, let me put a bar over to indicate their vectors. The direction vectors in planes sort of play the role of the slope of lines. Okay, so this direction vector is going to be 0 minus 1 is -1, 1 minus a -2 is +3. There's my eraser. Almost did a negative there. 3. And -1 minus a -3 is +2. So that's this direction vector, and then this direction vector is going to be 1 minus 1 is 0, 0 minus 2 is -2, 0 minus a -3 is 3. And of course, you could take this vector or this vector or this vector or this vector. It doesn't matter. You get 2 direction vectors there, any 2 direction vectors there. So if we could start at this point, 1, -2, -3, add a constant multiple of the 1 direction vector, and then a constant multiple, some other constant multiple of another independent direction vector. This vector would be a vector that points at the plane. And so by taking all possible values of s and all possible values of t, we're going to sort of sweep out or color in that entire plane. So if you say x, y, z, the vector is equal to this. This is the plane in vector form. So this is an equation for this same plane, the plane whose graph is this, in vector form. And from this, we can get the plane in parametric form. So you'd get x equals 1 minus s plus 0t, y equals negative 2 plus 3s plus 2t, and z is equal to negative 3 plus 2s plus 3t. So x equals 1 minus s, y equals negative 2 plus 3s plus 2t, z equals negative 3 plus 2s plus 3t. So there's your plane in parametric form. And this is called general form. So we have three ways, and I'm being a little bit lazy. I'm saying we have the plane in vector form. It's not really the plane. It's an equation for the plane. The plane's a physical object, not some algebraic thing. So this is an equation for the plane in general form. This is an equation for the plane in vector form. This is a parametric representation of the plane. Now, let's go back here and look at this general form again for just a minute. Because I want to note something. If we make a vector out of these coefficients on x, y, and z, so 5, 3, negative 2, and we look at the direction vector here, where is it? This direction vector, negative 1, 3, 2. Something interesting will happen. And that is, you take this dot product, you get negative 5 plus 9 minus 4 is negative 5 plus 9 is 4, minus 4 is 0. And similarly, if you take the other direction vector and dot it with this vector that we built from these coefficients, what's the other direction vector? We have 0, 2, 3. That's going to be 0 plus 6 minus 6 is also equal to 0. And so what we have is that these direction vectors are perpendicular, orthogonal to this vector that's built out of these coefficients. So that means that this vector is perpendicular or normal to that plane. So the normal vector, we call it n, is equal to 5, 3, negative 2. And so that's an interesting fact that we can use to come up with equations for planes. So if you have a normal vector to a plane, you take and dot that normal vector, 5, 3, negative 2, dotted with x, y, z, is going to be equal to that normal vector, 5, 3, negative 2, dotted with the vector built out of any point on the plane. So if we take this point right here, then you take this dot product, you're going to get 5x plus 3y minus 2z, that, is equal to 5. That's that. So this is in, what is this called? This is called point normal form. And so you have 4 different ways to write equations for planes in 3 dimensions. The general form, the vector form, parametric form, and point normal form. Okay, very good.